Welcome to the Ivy Hogwarts of 아이비셉트. 자, 오늘은요, 여러분들의 이해도가 어떻게 gradually upgrade 할 수 있는지 재미난 문제로 영상을 준비했습니다. 5점짜리 문제, 6점짜리 문제, 이해도가 7점짜리 문제들이 어떤 유형이 있는지에 대해서 배울 거예요. 왜냐면요, 여러분, 나는요, 여러분, 예를 들어서 등차 등비수열을 배웠어요 라고 했다고 하는 것은요, doesn't imply, okay, you solve every kind of questions that is related to the arithmetic or geometric. 그래서 수학은요, 어떠한 포뮬라를 배웠다라고 하는 것보다도요, 그 문제 유형의 여러 가지 종류의 문제를 풀어봤어요가 훨씬 더 맞는 정답이에요. 아시겠죠? 그래서 오늘은 같은 수열 문제더라도 그게 어떤 이해도에 따라서 5점 이해도, 6점 이해도, 7점 이해도에 따라서 어떤 식으로 바뀌는지에 대해서 이야기해 드릴 거예요. Like a sorting hat in Harry Potter. 그래서 제가 여러분들한테 이 내용에 대해서 원활하게 이해를 했다라고 하면 5점 기숙사에 배정을 해드릴 거예요. 6점 이해도 문제를 원활하게 풀으셨다 하면 6점 기숙사, 그 다음에 7점 기숙사 이렇게 가겠죠. 여러분 어디로 가고 싶으세요? 당연히 7점 기숙사를 가고 싶겠죠? So let's please try our best to get into the house of 7. Okay? So without further ado, let's get started. 네, 첫 문제는요, Arithmetic Sequence and Series에 대해서 한번 볼 거예요. 같이 한번 보시죠. So what is the general formula for the sum of the first and odd integers? Okay? 그러면 series가 어떻게 되겠어요? 1부터 12-1이 나오겠죠. And you know what? I want you to think about it. 이런 문제를 여러분들 이제 DP1, 여러분 고2가 올라가잖아요. 근데 이걸 푸는데 한 번도 가우스가 7살 때 1부터 100까지 어떻게 셈을 하는지 안 들어봤다? 그러면 안 돼요. Okay? Let me be honest with you. 그런 anecdote도 한번 들어보면서 이러한 포뮬라, 이러한 theorem에는 이러한 historical story, background story, anecdote가 있구나. 그래서 이런 걸 배우는 데에서 내가 즐겁다라는 이 취미를 좀 붙이셔야 돼요, 수학에. 그래야지 어려운 거 배울 때도 재미는 안 납니다. 왜냐면요, 결국엔 수학은요, it's a history of learning smart people back in the day. Okay? 결국 그들의 이제 의지를 잇는 게 수학이다. 라는 것을 말씀드리면서 한번 이야기해 볼게요. So the very first elementary proof, of solving this question of generalizing the formula will be the following the Gauss method. 그죠? 가우스가 1부터 첫 번째부터 끝까지 더했다는 거는 이제 더하기는 순서로 바꿔도 되잖아요. Which we call it commutative. 그럼 이번에는 첫 번째부터 n 번째까지를 더하는 게 아니라 n 번째서부터 첫 번째로 이렇게 reverse order로 할 수가 있겠죠. Right? And then even though we change the order because of the commutative property, they do have the same sum. 그죠? 그래서 이들을 더했을 때 어떻게 되겠어요, 여러분? Well, the s is gonna be double, so I have a 2s, right? 자, 그런데 여기서 여러분들이 페어해 보시면요, first term, last term, second term, second last term 같이 한번 더해 볼까요? 더하기가 하면 어떻게 되죠? I have 1 cancel out 되고요, 3 cancel out 된답니다. 그럼 2n이 계속 n번만큼 더해지게 되겠죠. 그래서 2n 더하기 2n 더하기 n번 하니까 we can actually multiply by n, which then results in the 2n square. Then I want to simplify for the s, so what we want to do is to divide by 2 on both sides. If I did, then I get the s to be the n square. That's one of the most elementary proof that we learn for the arithmetic sequence and series. And this will be the 5점 understanding. 자, 근데 여기서 여러분들이 약간 6점의 understanding 하고 싶다? 그러면요, 뭐 하셔야 되냐면요, any proof, any theorem, any formula you learn in IB, you should really try to consider deriving in a different way. 뭐 이런 것도 결국은 algebra를 이용해서 했지만 you should be interested in deriving the formula using the geometry, because mathematics is all about the visualization in 2D or 3D or 4D. 그래서 다음 포뮬라를 2D visualization을 어떻게 derive 할 수 있는지 한번 재미난 영상을 같이 한번 보도록 합시다. So 6점 understanding will be this. 나는 이렇게 1이 있어요. 그리고 1 unit square로 내가 assign 했습니다. area를 아시겠죠? 그 다음에 our formula was to add of the addition, the series of the odd numbers. 그죠? 그러면 1하고 다음 숫자는 어떻게 되겠어요? 3이 되겠죠. 그러면 3이라는 숫자에 상응하는 area는 3, 뭡니까? units of square. 근데 테트리스처럼 저렇게 기역자 모양으로 만들었어요. If you add together, it becomes a 2 square. 그죠? Okay, that's interesting. Maybe I can do the same thing for the 5 units of a square. 그죠? Which will then become the 기역자 of the Tetris. And if you add, I expect to have a perfect square. Let's try to have a look at this visualization of this summation. Okay? So now I'm going to add by 5. And now if I make the 기역자, then boom, I got the perfect square of a 3. Okay, you can then continue on and on and on. We can have the series of 7 and 9, which will still result in the sum of the integer square, right? So if I add by the 7 and make the 기억자 and boom, make a Tetris, then I got the 4 square. And maybe I can do this another one as to be, for example, the 9, right? Then I have the 5 square of the 5 units of the square. Okay. So 이런 식으로 이렇게 visualize 해서 inductive하게 approach 할 수가 있겠죠. What you just did is called inductive approach. You go one by one, find the pattern, and you make then final claim. Then I claim here, okay, I've tried with the, 몇 개의 sum 했어요. I tried with the 5 terms of the series and I found the pattern. Then I claim that the sum of the odd integers is going to be the perfect square of n. Is my claim. 뭐 증명하진 않았죠? 이런 식으로 approach 하는 거는 또 다른 proof 방법을 사용한답니다. Which we call it proof by induction. So what I'm saying here is, if you really want to go from 5점 to 6점, you shouldn't look at unidirectionally, right? 무슨 얘기냐면요, 어떤 거를 증명하거나 이해하려고 할 때는 여러 가지 방법들이 있나 없나를 고민하셔야 돼요. 그래야지 문제 유형도 한 문제를 풀 때 다른 방법들에 대해서 알 수가 있고요. 그 방법들 중에서도 가장 most efficient, 효율적인 방법을 선택하셔야 되는 게 수학이에요. 아시겠죠? So that's great. So that was the 5점 to 6점 transition of algebraic to the geometric. And you know what? Why don't we have a look at one of the most renowned formula for the sequence and series, which is the infinite geometric series. If I tell you what is going to be the infinite geometric series, I know for sure you're going to tell me a first term of the 1 minus common ratio r. I know you're going to be able to tell that because you've been memorizing it. 그죠? 근데 아이비 수학에서는 되게 중요한 게요. 이런 거를 어떻게 해요? 외우는 것만이 아니라 증명도 하셔야 된답니다. And why don't we have a look at the proof of this using the geometry again? Okay, 자 이번 것도 한번 geometric approach로 한번 증명을 해보도록 하겠습니다. Let's take a look. So you know what I'm going to do? I'm going to create a 1 length, unit length 1. But I'm going to make a congruent length here and keep multiplying the common ratio of r, that is between 0 and 1. Okay? 근데 common ratio가 0부터 1 사이니까 adjacent length는 계속 작아지겠죠. But I keep adding, so it's getting bigger. So I make this large triangle. Okay? So that's beautiful. And what I'm going to do is I make the congruent length of each adjacent, so to speak, and then make it perpendicular foot. Okay? And then I'm going to color this. Well, they are the same length, is to indicate. And I'm going to color this right angle triangle. 되게 중요한 게 뭐냐면 여러분, 이제 막 여러분들이 뭐 아이비 수학에서는 5개의 토픽이 있죠. 뭐 there's algebra, 뭐 function and equations, and trigonometry, geometry, and probability and statistics, and calculus. 가면 갈수록 여러분들이 그 전에 배웠던 것들이 굉장히 중요해져요. 막 circle theorem, 뭐 deductive geometry, 혹은 뭐 similarity, congruence, etc. 그런 걸 까먹으시면 안 돼요. Likewise here, when you see a right angle triangle, the very first thing you should really remind yourself is about the similarity 혹은 congruency. 우리가 뭐 8, 9, 10학년 때 삼각형 엄청 많이 배웠잖아요. 그런 게 결국 나중에 11학년, 12학년 때도 이어지게 된답니다. So should you not forget about those, okay? So that is great. So what I'm going to do is I'm going to reduce the size of this triangle, which is still similar. Why? If you ask me why, well, I got a share angle, 그죠? And I got a right angle here. And then by the alternating angle, zigzag, it's going to be the same angle also. Okay? Oh, 미안. I don't think we call it alternating angle. This is going to be a corresponding angle. So nevertheless, this is going to be the same angle here. So all the angles are the same. The ratio must be preserved, which we call the similar triangles. That is great. And I'm going to rotate this by 180. And you realize if I do the Tetris again, I have a circle, I have a square, I have a unit square length 1. Okay, so that is beautiful. So I can call this to be 1. Okay, then the remaining length, which we call the opposite, if I call this to be theta, is going to be 1 minus r. Okay, so you got those lengths. And then, of course, we can use the similarity using the SOHCAHTOA. Okay, that is great. So now I got the length here as a 1 minus r. And I told you, as we define here theta, you can use a SOHCAHTOA. For me, let me try to use a cotangent, which is the reciprocal of a tangent. It's not rise over run, it's going to be run over rise because it's the reciprocal of a tangent. So if I use the cotangent ratio on the blue right angle triangle, I have 1 over 1 minus r, which is the very formula of the geometric infinite series. And that is beautiful. But well, the ratio must be preserved by the similarity, and I can use the, what is it? The cotangent of the big right angle triangle, which is going to be the summation of all the terms and the adjacent over the over 1, which will result in the formula, the proof of the formula of the infinite geometric series, which is very nice visualization approach of the geometric series. So what I'm trying to say here is, just because you want to transit from understanding 5 to 6, I'm not asking you to memorize more formulae. But what you should do, what you should be able to do, is to be able to bring out those formula back in the days, what you have learned in the 8th or 7th or 6th grade, and still be able to apply to the understanding that you'll be learning anew later on accordingly. Okay, so that is also a very important 준비물, okay, preparation of achieving standard 6 in the HL. Okay, solid 6 in HL. So that is great. Let's move on to the 7 understanding questions of the IB, which you will be encountering very soon. Okay? 그러면 맞아요. 등차등비 우리 많이 배웠잖아요. 그런 문제들 말고 다른 본 적도 없는 sequence series가 나올 수도 있어요. In a very difficult question of a paper 1 or a standard question of a paper 3. 그런 series에 대해서도 같이 한번 이야기해보는 시간을 갖도록 합시다. So this is the typical paper 3 problem from a textbook. Okay, I believe it was from Hodder, which is a great book. But for part A, we already did that. We already derived the general formula of the arithmetic series in the first part of the video, so I will skip that a bit. So you can accept this to be true. It's free for you, all right? We already proved it, no problem. What I'm going to emphasize is a part B, okay? Because this really puts the emphasis of approaching mathematical question. They ask you to take a different approach, but still make the equation to be the same and derive something useful, okay? 자, 처음 거를 한번 보도록 할게요. Well, sorry about the typo. It's supposed to be R equal to, right? It's the index of a sigma, isn't it? So from first term to the nth term of that series, I want to have a different expression, but still make them into equal to, because that's the beauty of the equivalence, isn't it? So that you can derive something related to each other in a different format. 자, 여기서는 맨 처음은 어떻게 볼 수 있을까요? The standard way is to realize that this is a difference of cube, isn't it? And I really hope that you are comfortable of difference of a square or cube, right? That's the spirit of a 수학의 정석, isn't it? 그래서 한국수학교 10학년, 9학년 때 연습했던 게 또 빛을 많이 보겠죠. DP1, DP2 올라가실 때. So just to quickly remind you, A cubic minus B cubic 뭐였어요? A minus B times A squared plus AB plus B squared 되었죠. No problem, okay? And what I want to remind you here, I'm going to do the same thing on this difference of cube. So if I did, what do I have? I'm going to have R plus 1 minus R, right? That is great. And then I'm going to add by the R plus 1 square minus R plus 1, and then plus R square. Okay, so you can do the same thing. All right, so and I have expanded this one for you on the next slide. So let me quickly show you. So if I use the difference of cube inside, I get the following term. All right, the cube is going to cancel out, so it's beautiful. I got this quadratic term, no problem. Okay, another way that I'm going to expand, however, right, is to actually expand the sigma. Okay, why don't we expand the sigma? Because sigma is about the series, isn't it? So if I have a sigma, K는 1부터 n까지 있어요 of AK, and if you AK47, and if I put the K starting with 1, I have a A1, A2 going all the way up to AN. That's beautiful. All right, that is a beautiful. And if I do the same thing on here, what I'm going to have is, if you start plugging the 1, I have a 2 cubic minus 1 cubic. All right, and if I put 2, I got 3 cubic minus 2 cubic plus 4 cubic minus 3 cubic, and it continues on and on and on. If I go up to the nth term, my friend, I have a n plus 1 cubic minus n cubic. Okay, so that's how I'm going to list them out, just using the typical summation definition. This is just to plug it in from first term to the nth term and add them together. And on the next slide, I've done it for you. Okay, but I reorganized a bit so that it goes starting from the nth term, but you shouldn't change anything, because addition is a commutative. Even if you change the order, it stays the same. So I look at it. And what you are about to do is called a telescopic cancellation. And what it means is that you're going to perform the cancellation, and see any symmetry of it, right? So let's have a look. So if I look at the first two terms of that, the one common term is n cubic, which cancels out. I'm sure the n minus 1 cubic will also cancel out. And it continues on and on. Negative 2 cubic and 2 cubic will cancel each other. Very good. So the leftover symmetrically is the first term and then the last term. Okay? That cannot be canceled out because I don't have a 0th term here, or I don't have the n plus 1th term here because I'm adding from the first to the n. So that's the leftover. The leftover, my friend, is this. Okay? So this is the term I have. Okay? Which can be expanded, so I expand it out for using the binomial expansion, and boom, this is a simplified form of the series. All right, so that is great. So remember, where have I got this one from? The question have given me this identity, right? And what we have done before was just to use the difference of cube, then we derive r is equal to 1 to r of within 3r squared plus 3r plus 1. All right, so that was done by the difference of cube of the algebra within the sigma, just between the sequences, all right? But I also managed to expand this and then perform the telescopic cancellation and remove the sigma, didn't we? And then I have the n cubic plus 3n squared plus 3n. That is beautiful. And what is our aim? Our aim was to find the expression of the sum of the r squared, okay, which we don't know yet, you see? But now, using the different approach, but still the same thing, using this equivalence, you're about to achieve the aim that you wanted to. Okay, so let's take a look. Let's go further. So now I realize of that series, using the difference of a cube in that case will be the equivalent to the following form. Using the linearity of the sigma, I can apply the sigma from first to the third term. I took the sigma on each term, and now I'm about to apply the formula of the series, where for the second sigma we have an arithmetic series, isn't it? Which we derive algebraically and geometrically, thanks to the visualization of the video that Wonjun-san has prepared. Okay, so that is great. So let's move on to the next slide. So if I go to the next page, so that's the standard expansion that we did. But among them, who can you expand? I can expand the second term and then the last term, because the second term is just a simple arithmetic series that we already have derived, so we can use for free, which is the n times sigma of r will be the n plus 1 over 2, right? So that's beautiful. And if I go for the sigma of a 1, I'm just adding 1 n many times, all right? So which becomes just n, right? So that's why we have this n times n over n plus 1 over 2 multiplied by 3, and then the n. So far, so good. But you were comparing this also with the result that you have derived from the telescopic cancellation. So if I go to the telescopic cancellation result, which was, what was it? It was like n plus 1 cubic minus 1, isn't it? Then you can just isolate the perfect square term by doing the rearrangement, which I've done it for you. This is the result that we got it from the telescopic cancellation. I'm just canceling this term out. But of course, the mathematics is all about the beauty lies in the factorization and simplification. What I'm going to do is just put in the common denominator and then try to see any common factor and perform the factorization. Well, the obvious choice is the n, but within the bracket here, I got a quadratic term, and it turns out it is factorizable of the product of the n plus 1 and 2n plus 1. Then boom, 3 times the sum of r squared happens to be of that following form, where you can divide by the 3 to get the desired result of the sum of integers square. I know that you memorize this formula as soon as you read the formula, okay? In the 수학유정석 or any other book. However, the essence, the beauty lies in understanding how to derive it, because the method that you just did can be extended further for deriving the cubic sum or quartic sum, quantic sum, etc., which we can generalize and which we call it Fauer-Haber's formula, which is an exceptionally amazing choice of a topic for the internal assessment. All right? And has been twice in paper 3 with this related topic. So should you please learn this technique and be able to apply when the power raises to cubic 4, 5, etc. 아시겠죠? 근데 이런 식으로 해야 되는 게 이해도 7점이겠어요. 어떤 거냐? 주어진 정보를 적용시켜 주셔야 돼요. 내가 외운 거를 바로 발산하시면 안 돼요. that is memorization. That is not deductive science. Okay, what you have to show is, given the tools of the question, where they ask you to expand the sum of the r plus 1 cubic minus r cubic in two different ways, but they didn't tell you to expand which way, right? You came up with about the difference of cube as well as a telescopic cancellation. But if you ask me, how would I know that? Well, of course, it has to come from a tremendous amount of repetition of the work, okay? But we got it. 근데 뭐가 섭섭하겠어요, 여러분? If you do not prove this geometrically, that would be very 섭섭, isn't it? So I have prepared a geometric visualization of deriving this sum of integer square. Let's take a look. Okay. On the next slide, amazingly, what I have represent here is, okay, then let me try to put the 1 square as a sum of 1 unit square, 2 square as a sum of 2 unit square. So it's going to be, the area is going to be 1, 4, 9, and to the power of n, etc., etc. Okay, what I'm going to do is make a pyramid. But it's not going to be the pyramid that's going to be put into the apex, but it's going to be one-sided, sort of a slanted pyramid, okay? And you know what I'm going to do? You know what I'm going to do? I'm going to actually make 3 of these, just like the volume formula that you know, don't you? Because if you try to find the volume of a pyramid, what do? You do the base area times height over 3. Same understanding applies here. I'm going to multiply this by 3, okay? And then you can sort of realize that I'm going to actually divide it by 3, right? So I did that. And if I do so, I can make a puzzle. I can make the jigsaw puzzle of a 3D kind and try to make a volume out of it. And this technique is very similar to what you have learned from the completing the square. Remember the good old days of when you had to prove the discriminant and the quadratic formula? Actually applies to the completing the cubes also, right? Another IA clue. But anyways, let me try to add them together and I'll show you visually that it's almost a perfect cube. So I rotate it a bit and then make a jigsaw puzzle, then boom, of the other kind, and it almost completes the 3D shape, like this. But 아쉽죠? 이 부분이 비어 있잖아요. And it turns out, if you actually make a duplicate of this and then add it together, it becomes a perfect cube. So let's take a look. Boom, yeah, is what we have. And I want you to realize what we came up with was the I believe it was n, right? But then, if you look at the dimension, it's going to be, this is n, right? Was it? And then, yes, we added by 1 unit here because it has to be like slanted up. It needs to be perpendicular up. So I added by 1. And then the reason it got 1 unit further because I believe this was empty, wasn't it? Right? So if you double it, you still have to make account for the 비어있는 층. It's an empty floor, it was. But I added together so that it becomes a juxtaposition. So the height here becomes 2n plus 1. Oh my God. And if you actually multiply all together, we'll account for the, what is it? The volume of this cuboid. That's beautiful. But then what we were interested in was a sum of integer square where I'm going to divide it by 6. All right, so that sigma represents the sum of integer square. And what we can do is to put that dimension of the volume divided by 6 to account for the sum of integer square. That is going to be the visual approach of this formula. The reason I came up with this formula is that it could be obviously on the paper 3 of this visualization. And also, I want to remind you, like I said before, this sort of adding the extra pieces. Alright, you actually have seen it from the completing the square. And adding this extra cuboid to make a perfect cube of a bigger kind is a general approach to deriving the Cardano's formula that you have learned from the Veritasium video. Okay? So again, you know, of learning this type of a algebraic or visual different approach gives you different perspective, and that is the 7th understanding of the mathematics. All right. So here's the thing: just because we have learned the sequence of arithmetic and geometry doesn't mean you have learned it. What you should do is to try to attempt as many different kinds of questions as possible related to the same topic of sequence and series, and see yourself whether you can get them or follow them well. Okay, so this is the visual demonstration of filling up those gaps, completing the cubes, all right? Deriving the sum of integer square. It's a beautiful, beautiful demonstration, okay? 가 오늘까지 준비한 영상입니다. 이런 것들에 대해서 우리가 여름방학 동안 많이 배울 거예요. Which is we call it intensive class. Okay? I don't want you to come to the school. Okay? Come to the academy and expect to be listened. Alright? I don't want you to just sit there and listen to the class. What you should always do is to prepare the lesson and try to ask many questions as possible. Because one student brings one question, we can extend that question into at least 100 different questions, right? So based on the student's question and curiosity of a certain topic, even if you have learned the sequence series, can be expanded in a bigger scale like what we have seen today, okay? So 이런 algebraic approach만이 아닌 visual approach도 선생님이 많이 준비했으니까 이런 것들을 여름방학 때 같이 한번 많이 볼 수 있는 기회가 많은 여러분들과 있었으면 좋겠습니다. Okay, so that's pretty much it for me today. I will see you next time. So 오늘 영상 끝까지 보신 분들은 어디로 가요? 7 기숙사에 가도록 할 거예요. Okay, house 7 of 아이비셉트. That's it for me today. See you next time. Thank you.